Section 9-6 is on integration by trig substitution. The objective of this section is to simplify the integral of a function containing the square root of a binomial using a trig substitution and then integrate. So you've already seen several different types of techniques that involve a substitution. You've already seen variable substitution, or what we call a U substitution. You've now worked with integration by parts, which is in essence a substitution problem. You're replacing U and dv with something. And now we have this integration by trig substitution. All right, so let's take a look at how we use it. First of all, a trig substitution means that you're going to use right triangle trigonometry to substitute for some form of the square root of x squared plus a squared, or the square root of x squared minus a squared, or it could be the square root of a squared minus x squared, where a there is some constant. And when it says some form of that, it could be some power of this. So it could be that quantity squared or that quantity cubed. Of course, if you square a square root, then you don't even have a square root in there. It's just x squared plus a squared or whatever. All right, so let's take a look at these three different scenarios here, these three different cases, and what it looks like for the right triangle trigonometry here that we end up with. So, all right, so this first case here, we'll call this case 1. And you can see we've got a right triangle over here on the left, and it's got an angle there of theta, and a horizontal leg of a and a vertical leg of x. Of course, if I have those two sides of a right triangle, those are my two legs, then using the Pythagorean theorem, we can calculate the hypotenuse. Turns out to be the square root of x squared plus a squared. So over on the right now, I've got a little bit of triangle trigonometry that I'm doing with that right triangle to come up with a replacement or a substitution for the square root of x squared plus a squared and getting it in terms of theta. We're doing a trig substitution here. So if I look at the hypotenuse there that involves the radical, and the horizontal leg of this, which is the constant, those are the two legs that I'd want to work with here. I always want to involve the constant in one of these. That the secant of theta, of course, is the hypotenuse divided by the adjacent side there. So it's going to be the secant of theta is equal to the square root of x squared plus a squared divided by a. Or solving for that square root, it'd be a secant of theta is equal to the square root of x squared plus a squared. So if I had that square root right here in my problem, I could now replace it with a secant of theta. Now, of course, if I'm trying to do a substitution, I not only have to find out what I'm replacing that x part with, but I also got to find out what dx gets replaced with. So if I use the other two legs here of my triangle, the opposite side and the adjacent side, the vertical leg x and the horizontal leg a, again, always involve the leg that has the constant on it when we do this. You'd have tangent of theta is equal to x over a, or solving for x, you'd get a tangent of theta is equal to x. And then if you were to take the derivative of that to find the differential, really is what we're taking, finding the differential of both sides of that, you'd end up with derivative of a times the tangent of theta is just a times the secant squared of theta times d theta. And over on the right side, you'd have dx when you take the differential of x. And so now I would have a substitution for dx. Those are the two basic components that I need. I need a substitution for that square root of x squared plus a squared, and I need a substitution for dx. And I have it now in terms of theta. Now the idea is that I'm going to go from a function that I can't integrate that involves one of these radicals, one of these square roots, and rewrite it in terms of some trig functions that I can integrate. And if you recall, in the last section, we learned about how to integrate the powers of trig functions. So I should be able to use some of those techniques to help me evaluate this. All right, that's case 1. This is what happens if you're working with the square root of x squared plus a squared. That turns out to be the hypotenuse. And notice that we end up doing a substitution that's going to involve secant and potentially tangent. Okay. All right, let's look at case number 2. Case number 2. Here's the same triangle basically, but we've moved around a couple of the sides. Now we're putting a on the horizontal, that's where it was before, and x on the hypotenuse. Now if I have a on the horizontal leg there and x on the hypotenuse, then again using Pythagorean theorem I can find the measurement of that third side, that vertical leg. It's just going to be the square root of x squared minus a squared. Okay, and once I have that set up, I can then again find the relationship between that square root as well as dx. So let's start with that square root part first. The tangent of theta would involve the opposite side and the adjacent side, the vertical leg and the horizontal leg. Again, you always want to involve that leg that has the constant on it. So tangent of theta would be the square root of x squared minus a squared over a, or solving for that radical there. A tangent of theta is equal to the square root of x squared minus a squared. So I now have a substitution in my problem for this quantity, square root of x squared minus a squared. It would be a tangent of theta. And now I also need to find out what dx is equal to, so use the other two legs here, actually the hypotenuse and the adjacent side. Again, the adjacent side is a side that has the constant there. That's what we always want to include. So the secant of theta would be x over a. Solving that for x, a secant of theta would be equal to x. And now to find the differential of x, I got to take the derivative of both sides, or the differential really of both sides. So it's a times the derivative of secant is secant of theta, tangent of theta, d theta. And that's equal to, the differential of x is just dx. And so now I have a substitution that I can make for my dx in my problem. And get it all in terms of theta. That's the whole idea. We're replacing some function that involves this radical, some integral that involves the square root of x squared minus a squared, and replacing it with some trig functions. All right, in this case it would involve, again, secant and tangent of some sort. All right, let's take a look at the last of the three cases. And the last of the three cases looks like this. This was the case where it's the square root of a squared minus x squared, so it's the constant squared minus x squared. Again, the triangle looks very similar, but now we've got x on the vertical leg and a on the hypotenuse there. And so again, using Pythagorean theorem, we can find that the horizontal leg here would be the square root of a squared, the hypotenuse squared, minus the x squared, the vertical leg. And again, now if I want to find what that radical is equal to in terms of theta, that's on the horizontal leg, and use the leg that has the constant, or actually it's the side with the constant, that's the hypotenuse. So that's the adjacent side and the hypotenuse. That sounds like cosine. Cosine of theta is equal to the square root of a squared minus x squared divided by a, and solving for the radical, a cosine of theta is equal to the square root of a squared minus x squared. So again, if I had this in my integral that I was trying to evaluate, I could now replace that with a cosine of theta. Now again, I've got to find out what dx is equal to, so use the other two sides of my triangle here, the vertical leg and the hypotenuse, to find that. Sine of theta is equal to x over a. Solving for x, you get a sine of theta is equal to x. And now take the differential of both sides, and we'll get a cosine of theta d theta is equal to dx. And once again, we've now come up with a substitution that we can make for the dx in terms of theta and d theta. And so again, this technique you can see, or this type of problem, is going to involve rewriting that radical in terms of some product of sines and cosines. And again, the idea is that hopefully I can evaluate that integral now. All right, now these three cases that we just went through here, those are good. I think those kind of help show you the different scenarios here, but it's not a case that you should be memorizing these three cases. That's not what the point of this was. It was just to show you what this looks like. But rather, we can actually come up with kind of a list of rules here that we're going to follow as we go through this. And this is basically, I would suggest to you, is the better way to try to remember this. This is how you want to set up your right triangle every time that you do this. And basically, you need to sketch a right triangle and actually write on that right triangle the legs of it and the hypotenuse, label those sides, and then actually write down your trig evaluations, your trig equivalents. So if the radical contains addition, that was the first case, case 1, it was the square root of x squared plus a squared. Then the radical is the hypotenuse. Otherwise, the radical is going to be a leg. So that's the first thing. Look for whether it's addition inside that square root or whether it's subtraction. Addition means you found the hypotenuse. It's sitting there in front of you. Secondly, if the x is a leg of the triangle, then you want to put x on the vertical leg. All right, so if you can, put x on your vertical leg. And then the third rule here, basically, that we're going to follow, if x is the hypotenuse, then put the radical on the vertical leg. All right, and that was kind of like the second case that we saw there. X was the hypotenuse, and so we had the square root on the vertical leg. All right, so if you remember those three rules there, those pretty much tell you how to set up the triangle that you want every single time. Now it turns out, obviously, you can switch around the two legs of your triangle and it doesn't change much in your problem, but however, it does change the trig functions you come up with, and therefore can make the problem a little bit more difficult. The whole point of following these three rules here is that it will always involve either secant and tangent like you saw, or sine and cosine. And it's in the order that we did those. If you switch those around, then it's going to be a little bit more difficult. In particular, you're going to get those negative signs to show up when you go to start taking derivatives and antiderivatives and so forth. All right, so here's the method that we're going to follow each time. Let's try this out on an example. Look at example 1 there. They ask us to evaluate the integral of dx divided by the square root of x squared minus 9. Now, again, my thought process here when I look at this radical to begin with is this. I'm looking at this square root and I'm thinking, man, I think I could actually draw a right triangle that would have one of the sides of that right triangle being the square root of x squared minus 9. And of course, saying that and then actually sketching it. So let's see if we can actually sketch this triangle out and see what we end up with. So if we were to sketch this triangle, call this our angle theta. Now, actually, to set up your three sides of your triangle, they're all actually written right here in the square root of x squared minus 9. All three sides are given right there. But the way that I'm going to set this up is by first looking at the fact that it's a square root of x squared minus 9. So the fact that it's subtraction tells me that this does not go on the hypotenuse. So the next thing to consider here is looking underneath that square root. And whatever that first term is, it's x squared in this case. The x squared is telling me what the hypotenuse is. So this guy right here is the hypotenuse. The fact that it's subtraction, and then whatever the positive term under there is, that's what tells me that that's the hypotenuse. The hypotenuse is going to be x, which when he said when x was going to be the hypotenuse, then we want to put the radical there on the vertical leg. So the radical here is square root of x squared minus 9 goes on the vertical leg. And then the other leg is going to be basically sitting right here, this 9. This is our horizontal leg. It's not 9 though, just like the hypotenuse was not x squared, it's the square root of that quantity. So the horizontal leg is going to be 3. Okay? So again, when you look at that entire radical there, all three of those sides are determined right from that radical. Now that I've got the triangle drawn, I can actually go and find what my radical is equal to. So I'm going to start out with the vertical leg, that's got the radical on it, and my horizontal leg, because that's got the constant. That's what we said, always involve the constant when you set this up. So that sounds like opposite and adjacent sides. That sounds like tangent. Tangent of theta is equal to the square root of x squared minus 9 divided by 3. And solving for that radical, you have 3 tangent of theta is equal to the square root of x squared minus 9. Now again, I'm not memorizing those 3 cases that I had on the previous slide. I'm just simply drawing the right triangle and then using it to come up with this. So it's not a case that I got to memorize anything as far as the what tangent of theta is equal to here. But rather, the memorization that I got to do is I got to know where to put the sides of this triangle at. Which part is x, which part is the 3, which part is the radical. Now the other part of this that I need is you can see I've got now the substitution for this guy. I don't have a substitution for the dx. So I'll use the hypotenuse and the horizontal leg. That sounds like the secant of theta is equal to x over 3. Solving for the x, you have 3 secant of theta is equal to x. We always want to solve for x. And now take the differential of both sides to find out dx. Derivative of secant is secant tangent. So it's going to be 3 secant of theta, tangent of theta, d theta, and that's equal to dx. And now I have a substitution over here for the dx that's in the numerator. So now we are all set to do our substitution. So instead of the integral of dx in the numerator, let me just rewrite this. Dx gets replaced with 3 secant of theta. Oops, secant of theta. Tangent of theta times d theta. And that's all divided by that square root of x squared minus 9. And that we said over there was equal to 3 tangent of theta. Divided by 3 tangent of theta. Now some nice things happen here when we end up with a problem that involves division like we did here. It was dx divided by something. And notice what happens here is the 3's cancel out. In fact, the tangents cancel out. That's going to happen every single time that's going to involve at a division like this. It's going to simplify in some way. In this case, it simplifies down to just the integral of secant of theta. Okay. Now, before you integrate this, again, you always want to, after you've done some sort of substitution like this, go back to the original. I started out with this function here that I could not integrate. I don't have a technique to integrate it. Now I write it in terms of just secant of theta. Well, I know the rule for the integral of secant. In fact, we just talked about those back in the last section there, section 9.4. So I know this, I can evaluate it. As long as you can evaluate it, you're good. Again, the technique to help you remember these rules, remember your derivative rules. Derivative of secant is secant times tangent. So the antiderivative involves the same 2 trig functions. It's the natural log of the absolute value of secant of theta plus tangent of theta. Again, if you don't remember those 6 rules there for your integrals of your 6 trig functions, you got to go back and review those. You need them. And now I've got this answer here in terms of secant of theta and tangent of theta. Well, I started out with a problem in terms of x. I should write my answer in terms of x. So I got to go back and find out what secant of theta and tangent of theta are equal to. Well, I actually already wrote those down over here. Right here is tangent of theta. Here's secant of theta. So all I have to do is substitute those guys in. So let's replace the secant of theta with x over 3. It's the natural log of the absolute value of x over 3. And the tangent of theta we said was equal to that square root of x squared minus 9 over 3. Square root of x squared minus 9 over 3 plus c. And you can leave your answer just like that and be done. You don't need to go any further with it. However, the book is going to go a little bit further with these, so I'm going to just show you what the steps are that they're going to use to get their final answer, just so you can recognize that. So inside of this absolute value, you can see you have a common denominator, so I'm just going to combine those 2 fractions and write as the natural log of the absolute value of x plus the square root of x squared minus 9, all divided by 3, plus c. And now I have the log of a quotient. We have a property for the log of a quotient. We know the natural log of a quotient is equal to the difference of the logs. I can rewrite this as the natural log of the absolute value of x plus the square root of x squared minus 9. And then, oops, not plus, but minus, since it's a quotient, the natural log of the absolute value of 3. Of course, absolute value of 3 is just 3, so you can get rid of the absolute values if you wanted to. And then plus c. Now, this quantity right here, natural log of 3, is just some number. It's a constant. So what I could do is I could combine it with this constant. In fact, I'll combine it and give it a new name. So I could rewrite this as the natural log of the absolute value of x plus the square root of x squared minus 9, and then plus c1. All right, so if you're looking at the, if you're checking your answers in the back and you're wondering how they went from this answer that you got at the top to the answer they're going to show you in the book, which is what we have here at the bottom, how they get rid of those 3's, well, that's what the trick is. They've used the log of a quotient property and combined that denominator, that constant, with the plus c. All right, let's take a look at another example. Look at example 2 here. It says evaluate the integral of dx over x squared plus 37. Now again, this is it doesn't quite look like it fits the kind of problems that we're talking about in this section, but let's rewrite this just slightly. I can see that it's got an x squared plus 37, so it kind of looks similar to problems I've seen in this section, but I'm going to rewrite it this way, as the square root of x squared plus 37, and then square that quantity. Those two, of course, are the same thing. When you take a quantity and take the square root of it and then square it, you get that x squared plus 37 right back. But now I can see that I've got that square root in there. If it helps you to rewrite it, do so. It's obviously not necessary, but you should recognize the fact that it's x squared plus some constant. It doesn't have to be some constant, some perfect square, just plus some constant. That's going to involve this technique. All right, so let's draw our triangle. And because of the fact that it's a addition there, it's the square root of x squared plus 37, that means that that radical goes on the hypotenuse. So that's this scenario. When that goes on the hypotenuse, again, sitting right here inside of this radical are the other two legs. This right here is a leg, and the 37, really the square root of each of these, are the other two legs. So sitting right there in front of me is the two legs that I need. I'm going to put x on the vertical leg. That's what we said to do. If the radical is on the hypotenuse, then you put x on the vertical leg, and put the square root of 37 on the horizontal leg. And again, double check that in fact this, using Pythagorean theorem, that this in fact gives me a triangle with that hypotenuse that we said. But square root of 37 squared plus x squared definitely would give me that hypotenuse. All right, so now let's find out what that radical is equal to. Again, we want the hypotenuse as the radical and the horizontal leg there is the constant. So that sounds like secant. Secant of theta is equal to the square root of x squared plus 37 divided by the square root of 37. So that means the square root of 37 times the secant of theta is equal to that radical, square root of x squared plus 37. Again, it's not a case that I'm memorizing those three cases. I'm just simply setting up the right triangle. I know that I do have to know how to set it up properly. But once I have it set up, I just simply use my trigonometry to come up with the relationship between that square root and theta. Now we're going to do the same thing to get x. And x is on the vertical leg there. So I'll use the vertical leg and the horizontal leg. Always use that constant. That's the tangent of theta, is the x divided by the square root of 37. And so the square root of 37 times tangent of theta is equal to x. And now find the differential of both sides. So we end up with the square root of 37 times the tangent of, oops, got to find the derivative of that. Derivative of tangent is secant squared of theta, d theta, is equal to the differential of x is 1 times dx. Derivative of x is 1 times its differential. And now I've got my substitution. So let's fill that in. So instead of the integral of dx that we have in the numerator, this is going to become the integral of dx is going to be the square root of 37 times secant squared of theta, d theta. And that's divided by that, it's that square root squared, remember. So I found the square root of x squared plus 37 was the square root of 37 times the secant of theta. And again, I have to square that quantity. All right, so let's simplify this first. So you actually have secant squared in the numerator, and it's going to be secant squared in the denominator. So those guys are going to just cancel each other out. And then you've got a square root of 37 over the square root of 37 squared in the denominator. So actually, the square root of 37 in the numerator cancels out with one of the square root of 37s in the denominator. I'll just cross out that 2 down there. So we actually have just d theta over the square root of 37. In fact, the square root of 37, that's just a constant. We could pull that out front. It's 1 over the square root of 37 times the integral of d theta. If it helps you to do it that way, then certainly write that out. But the integral of d theta is just theta. So we have 1 divided by the square root of 37 times theta plus c. And the last step is to go back and replace theta now with what it equals. Let's go back up here and look at our triangle. Now we found out what the secant of theta equals and what the tangent of theta equals. So I don't have what theta equals, but I do know that I can find theta from one of those two. And usually what we pick is the one that's in a simpler form. You can see that this has an x in the numerator for tangent of theta, versus this has that square root of x squared plus 37 in the numerator. So we're going to pick the simpler one, which is the tangent of theta, and rewrite it. So I can rewrite this as theta is equal to, just using your definition of an inverse trig function here, theta is the tangent inverse of x over 37, x over the square root of 37. And let's make that our substitution for theta down below. So theta gets replaced with the tangent inverse of x over the square root of 37 plus c. All right, and there is our antiderivative of that function. Again, we start out with a function that in the form that it's given in, we cannot integrate. U substitution is not going to work here. This is not a integration by parts problem. The only technique that's going to work here for us is to use a trig substitution. Now, I say the only technique, and that's not quite true in this problem. You may recall that you've seen the integral of, or you've seen the derivative of tangent inverse, which looks a lot like this original integral. And so that's why our answer turned out to be just tangent inverse, basically. Derivative of tangent inverse is 1 over 1 plus x squared. And so for that reason, we ended up with an answer that was very similar to just tangent inverse of x. All right, and that is the first half of this section.